Hello, everyone. It's very nice that you have come and you are not in the queue for a lunch so far. So I am Maciej and I am responsible for technical stuff in Code Heroes. A couple years ago, I was passionate about the Spring, Hibernate, blocking programming. I was really passionate about Java. But the problems I was facing is mainly solving the problems from the frameworks, facing the problems which give me the Hibernate to solve. So I tried to find another way of implementing application and be it more asynchronous, more reliable. So I tried to use reactive approach. And to reactive approach, we have some kind of architectural patterns connected, which is event sourcing and CQRS pattern. So maybe a couple of you or all of you are familiar with this, but at the beginning, I would like just to explain where from they come and to explain what they are. And after that, I will share my knowledge and experience, what I have learned so far from using it in our systems, in our software. So at the first, there's something called the domain-driven design. So what is this? This is just a kind of approach which tells the developer and the system architects, co-founders, owners of the product how to implement the software. And the primary focus of DDD approach is to focus on the core domain of our software. And it implies to focus on the interactive collaboration between the teams. And this domain-driven design was invented by Eric Evans, and there is a huge book which explains how to use it and what is this. But there are some kind of strategic patterns and tactical patterns. And here we will be talking about one of the tactical patterns, which is called Aggregate Root. Aggregate Root is just kind of a collection of objects which are bounded together, which cooperate together to implement a kind of part of our domain. And what Aggregate Root does, it guarantees that any operation which we made on the Aggregate Root is consistent, and the operation which is made over the Aggregate Root changes the states, mutates the states inside the Aggregate Root. And the Aggregate Root is the only one object in our domain which exposes the API to change its state. So suppose that we have a transaction aggregate root. So the transaction aggregate root is used for handling the transaction operation in our domain. So we can, and it exposes API of create transaction, generate our offer for transaction, approve the offer, pay for the transaction, and, for example, get status for the transaction. And this aggregate root exposes the API and expose the domain API for this. And inside of this, we can find another value objects and other entities like currency of the transaction, status, our price offer generated, exchange rate, for example, or payment. So this is aggregate root, and aggregate root is the kind of object which gather all the other objects, and this is the only object in our domain which exposes API to talk with our aggregate root here with the transaction. So we do not have setters, getters, all of this. The transaction is a typical object. It has an logic inside of this. We can test our aggregate root. And what we want to do, generally, you can have this transaction aggregate roots in the memory, but our systems and our clients require us to have some kind of persistence layer, so we would like to save these aggregate roots in the databases. So there are two approaches of doing it. The one of this is persistent state. So what does it mean? The persistent state is saving the current state of the aggregate to the database, to the repository. So we just make the snapshot of current state of the aggregate, we are saving it. So when we have some kind of command is this operation create, generate, approve offer. So first we need to get the latest step from the database, from the repository. We need to update, so we need to mutate the state, and we need to persist this. And what is the most problematic part of this is that when we are taking this aggregate root from the database, we need to have some kind of locking mechanism to prevent race conditions. So if we have a couple of threads which are making some mutable operations on this aggregate. So here's a part of code which can expose it. So we have a class domain service, and we have here an operation get offer for this transaction. So we load the transaction from the repository, we are invoking the method generateOffer over our aggregate root. It mutates the state, generates offer. So we are getting the offer, and what we are doing next, we are saving the transaction, and we are returning the offer. The problem is that if there is a repository and we have one and the second load, so we are loading the latest states of the transaction aggregate root from the database. And we have the version blue and the version green. And after that, there are two different threads which are invoking operation generate offer over them. And after that, we are trying to persist all of them. So finally, the last one will be persisted in the database. And this is the problematic, that we need to have some kind of mechanism for locking, for scheduling which operations and which thread should have access to this. Event sourcing is another approach. In persistent state, we are saving the latest state to the database. In event sourcing, we have event sourced entity, so our aggregate root lives in the memory, and we are not saving the persistent state, but we are saving the events which are the effect of applying the function. So the current state of the aggregate root is in the memory, but in the database we are collecting all the events which can be then read from the database. So it is called event reply. So we're replying the events. We are building the latest state in the memory, and we have this. The problem is here that even if we have this in the memory and we are saving only the events to the memory, so we are persisting the events to the database, so we're not the memory, we still need to have some kind of pattern which allow us to make a thread safe command handling over this. So this is an example of event sourcing. So we have a domain service, we have a get offer over the aggregate root transaction. So it's just a code which shows how it should work, but if you are using Akka, etc., it works totally different way. But what we are doing when we want to make some event sourced aggregate root, so we have the event store when we want to load the events for this transaction ID. We are building the transaction from events, so we have just a simple function which applies the events and builds the states. And finally, when we invoke the transaction generate offer, we have the offer and we have the new events which we need to persist as the result of our operation. So what are the difference? The persistent state, we are persisting the current state to the storage. In event sourcing, we persisting events which leads us to current state. The current state in the persistent approach lives in the database. The current state in the event sourcing approach, we have this in the memory. And in the persistent state, we need to mechanism to protect us from race conditions as regards saving state to the database. In event sourcing, we need to have a mechanism for protecting us from race conditions as regards handling and processing commands over the entity which we have in the memory. So here actor comes, and what is actor? Just a quick recap, is a primitive unit of computation, and actor receives the messages and make computation on it. So here we are making a computation. Here will be just generating the new events. Actor has a mailbox, so we have the queue of the new commands which we are handling, and actor is responsible for at this single and the one point of time process the only one command, and all the other commands are waiting in the queue in the mailbox. And actor can have its internal state, and actor lives in the memory. So here we can say there is a mailbox, there are new messages, new commands, they're coming to actor, actor is processing step by step every message, and we are generating, there is some kind of response. In our case, this will be generating events. So what is event source actor? So event source actors is an actor which handles commands sequentially. It persists events as the result of handling command, and it builds current state based on the events. It implements recovery mechanism after a failure or after we just shut down the system, because when we need to when we want to send some commands, for example, pay for the transaction to the transaction, we need to replay the events in order to rebuild the latest state of our actor in the memory. And after this replaying events process, we are able to process the command. Oh, so it's a little more complicated, but let's see. So this is just simple event source actor. In my presentation, I didn't want to focus on the Akka, eventuate, Axon, all these frameworks. I just want to make it framework, without any framework. So in our actor, we have some kind of state, which at the beginning there's an initial state. We have a recovery function, which means that every event we are recovering, we have a function handle events, which takes the current state. I don't know if it works. Nope. Maybe yes. No. So here we have a current state and the new event, and this function returns as the new state. So we are applying the new state to the state in the actor. And here we have a function which is receive command. So here is, for example, a command create client, and we are producing the new event. We are persisting this event, and after this, we need to update also the state. And this is our pure function, which is handle event. We get the state, we get the event, and based on the type of event, we are making some computation on the state. So we are creating the new state. So this is the simple concept of event-sourced actor. So this is all about event sourcing. So generally in event sourcing, we do not have a state in the database. We have the history, the log of events which are the result of handling the sequence of commands. And we need, in order to have the latest state of the actor, we need to replay all the events and have them and rebuild the state of the actor in the memory. CQRS, so it's a command query responsibility segregation pattern. So it separates the side of the command side and the side of the read side. And we can scale separately every of each model. The write model produces the events. So the write model will be this actor. And the read models are reading the events and builds its own view. And you need to deal with the eventuality consistency. And I will show the slide. I use the Axon because it's really cool as regards the slide. So how it works. We have a domain, and all the stuff above this line is the write side, and here we have the read side. The write side is responsible for handling the command, and we have also the event store when we're persisting all of the events. So when we send the command to the domain, to our actor, we are taking the actor from events from repository, we are replaying the actor, and we are making a computation, and after every computation, after every command handling, we are trying to persist events to event store. And here there are event handlers, so here is the read side. And here, for example, we can have many different models we have, because the models are built on the events we have persisted. So here, for example, we can have, if there is, for example, a model of transactions in some kind of stock exchange, so here we can have some kind of read model, the different process which is responsible, different application which is responsible for providing some kind of analysis on this data of the latest transaction. We can have some kind of database which is just a read model for the list of the transactions. And we have some kind of messaging read model which is responsible to send emails to our users for every transaction succeed when any transaction succeeds. So this is the main and the most important part of this, is that we have the write side which produce events, and we have the read sides can have as many as we want to have read sides, because each of these read sides can be a different application, and we are reading the events, so we are able to read all the events from our event store and replay them and build a new view. It can be a list, it can be some kind of cache, it can be just sending the messages. And the most important thing we need to know is something which is called eventuality consistency. So when we pass the command to domain and we persist the events, it's okay. Our domain is consistent, because if we make any request to the actor, we know that actor has this message mailbox, so we schedule all these messages and we are processing them sequentially, so we know that in the memory we will have the latest state of the actor. But the problem is that there is some kind of time, and it's called latency, between we persist the event to event store and the time when we receive this event here. So sometimes it can be something strange for our clients and for us, that, for example, there is a transaction and we send the command create transaction, and we persist the event that we have created transaction. But when you go to the list of transaction, you will notice that there is no transaction. Why? Because there is a couple of milliseconds, 100 of milliseconds, which takes the event to come from event store or event bus and come here. So it takes a couple of milliseconds. It's called latency time. which system needs to process the events and to build the view, to build, for example, the list. So it's really cool that you can separate it, but you need to face eventually consistency. So how CQRS fits microservices? So CQRS fits microservices because each model, write side or many of read models, can be just a simple microservice. And you can, what is very cool, you can have some kind of model declared between the team which is developing the write side and a couple different teams which are responsible of developing the read side. And each of team can use different technologies to implement different read models, to implement different things for your business requirements, because you can easily develop different microservices in your team. So CQRS is a really cool pattern for handling stuff in the microservices architecture. And how CQRS fits the polyglot persistence approach. So polyglot persistence approach is about using write persistent layer, so just write database storage system to business needs. And what is really cool in CQRS, when we are building a model, we can choose any database we want to. So we can, for example, use a Redis for some kind of simple cache. If we need, for example, you would like to have a search with quick search when you would like to search by prefixed strings in your website. So and you would like to do it by by the names of the user who has already created the transaction. So it will be really hard to do it on the right side, but you can implement the read model, which reads all the events connected with the transactions and build it in the Redis to have some kind of fast search. You can use MongoDBs for data which fits documents, and for example, you can use Elasticsearch to implement some more sophisticated searches in your system. So this is a recap, what is event sourcing, what is CQRS, and now I would like to share some kind of best practices. So, event serialization. At the beginning, when I start using frameworks, the info about event serialization is hidden really deep in the documentation, and this is the most important part, because if you don't think about this, you will end up with the system on the production, which will, for example, serialize your events with Java serializer. So this is the most important part, to be aware what kind of technique you use for serializing the events. Because if you persist the events as the result of some kind of command in your event sourced actor, in your code, for example, in Java or in Scala code, it will be the class. But you need to know how to serialize it to the database. So it is really important to choose a cross-language solution, because if you would like to have microservices, CQRS, all this pattern, you need to be conscious about the fact that, for example, one of the microservices will be implemented in Scala, another will be implemented in PHP, another in, for example, Node.js. But it's important that you share the same way how you persist the events. So the cool stuff we used is Google protocol buffers. They're really cool because they have a schema. And other guys use JSON. It's also okay, but I really prefer Google protocol buffers. Even schema versioning, it is also important, because if you have a couple of types of event sourced actors, and you are emitting different type of events, and you have a different type of microservices, and you rely on the same data, it is really important to have some kind of repository for your schema. And it is really cool to have, for example, the shared Git repository to save this schema inside and use this functionality. It's really cool because when you centralize the schema, everyone in the team can benefit of this, and every team can benefit of this. And if we make some changes to the schema, all guys on the other side, on the other team, will get it to know, because, for example, the Jenkins build will fail because there is the new field in our schema which we need to process in our system. Choose the great event store. So when you are designing this kind of system, you need to choose the event store which fits your need, because it's a crucial part of this. It should be scalable and reliable, and the most important fact is that you should have resources to be aware, and you should have resources to maintain this event store, because you can easily take any database you want to, but you need also be aware how to manage and do the DevOps over it. So as regards the event store, for this event sourcing approach, it can be, for example, SQL databases, Postgres. It can be NoSQL database. It can be Cassandra. You can choose any type of this. The most important fact is that it should be reliable, scalable, and you should be able to operate this. Okay, some kind of problems. Aggregate root is not an entity. So I mean that we should think about aggregate roots as something more sophisticated pattern. So, for example, we have exchange trading system for currencies. So there is a exchange rate exchange. When I am coming, I have euros, and I would like to exchange my euros for PLN, for Polish zloty. So and there is a trader who is responsible to get all these transactions and make some kind of process of settlement. So it means that I want to connect the sell and the buy transactions and connect them. And the business requires that we need to have guarantee that transaction can be part of only one settlement. The basic approach for implementing this is, for example, that we have a settlement aggregate root, we have transaction aggregate root, and another instance of transaction aggregate root. And the trader wants to make a settlement between those two transactions. So we will push the command create settlement. Settlement will try to settle transaction blue. We succeed with this operation, so we'll try to settle transaction green. But there will be a failure because maybe there is another process which has already settled this transaction. So what we need to do, we need to roll back the settlement. But the problem is, what happens if this rollback will fail? And this is the really, really big problem here. So what we can do, we can rethink our model and try to do something like this. Maybe as regards, this is the trading, so maybe we don't need the separate aggregate root for settlement transaction. Maybe we just we can introduce trading aggregate root, where we have settlement entity, transaction entity, and as I said at the beginning, aggregate root is responsible for guarantee the consistency of every inside of this. So we can just say settle. We can have the list of transactions entity. We can have a list of settlements entity. And we can go through, for example, settlements entity, find if these transactions are not already in any kind of settlements. If they are not, we can make a settle and succeed. So this is the most important part. You can do it this way and facing these problems, or you can do it this way. So remember, aggregate root is not an entity. So if someone is using aggregate roots and event sourcing, etc., or just have a lot of simple, smaller part of the domain which are just entities, transaction, settlement, user, etc., it's something wrong. It should be done like this. It should be done like this. Okay, facing unique guarantees. It's a headache. So we have event sourced aggregate user, because we decide that we would like to have our user implemented in event sourced way. We need to guarantee that the login and the email of our user must be unique in the whole system. So the problem is that aggregate root guarantees uniqueness only for the one of the identifier. So how it works? When we have the user and the identifier of the user will be the login, there is no way to guarantee that we have the email also unique in the system, because we are making the commands to the login identifier. So if you would like to, there is no place when we can check if the email is already. We need to ask all others aggregate root, hi guys, do you use this email already? It's terrible. What we can do here is, and this is also a problem with eventually consistency. So what we can do here, we have the user aggregate root, and we are sending command create. So we would like to create this user with login Maciej and email Maciej at codeheroes.io. And here we are sending the command to actor which is identified by login Maciej. But there is no chance to check inside the user aggregate, because it doesn't have a data, if there are any other users who are using the same email. So how you can do it? Of course, you will emit, as the result of this create, you will emit the email assign event. So we know that to this login we'll assign the email, and we persist this in the event store. And what we can do in our domain, we can have some kind of email service which will reply all this event and build here internal map. This is this email to this login. So when we improve implementation of our create method, create handling command process, before we emit the email assigned event, we can check the service, does this email already used exist? And it can say yes or no. So here we can have some kind of validation. But there is another problem, because when we persist this event, there is this latency, eventually consistency. So it also means that on this side, we can have the view that we have already created the user with this email, but it doesn't mean that this guy will know it. So in this kind of approach, there's a possibility that we'll have a couple of users with the same emails. So what in this way? What with this problem? We should have some kind of logic, some kind of process inside business process. What we should do in this kind of problem, because event sourcing is really cool, but if you would like to do it, do the simple way which you are doing in the MySQL databases before, it's a nightmare. Why does it work? But we benefit other things from this event sourcing approach. But still, we have a problem because we need to implement some kind of logic. Maybe when we receive the duplicated email, we should block this account, which is a duplicated account. This is the problem, and you should be aware if you are using event sourcing that you cannot guarantee uniqueness for a couple of identifiers, and you need to solve this other way. But sometimes you need to ask, perfect, I have the event sourced actor user, I have the history and every log of this, and I have the log history of every user in my system. And the chance that there will be a lot of users which will try to register with the same email is really, really low. So maybe I can agree for this, but I should think about this process, how to deal with this. Okay, transactional operations. So Aggregate Root is persisting the event into event store, but we also need to know, for example, we also want to publish this event to some kind of distributed queue in our system, because we want to tell other services that something happened in our system. So we want to have guarantee that this event will be also published in the queue. So simply, we want to have transaction or persisting and publishing process. This is the problem. So we create, for example, the user. So the first we persist the event to the event store, but we would like to also publish the event to the queue. And the problem is that this is asynchronous operation. So it's really hard to make a transaction between them, because maybe persist will succeed, but publishing will fail. So other parts in our system will never get to know that there is the new user. What with this kind of problem? We need to remember that our event store is the only source of truth in our system. So we can solve this problem in another way. We can create the user, persist the event store, and have some kind of queue service which is reading these events, so replying, and it will be responsible for publishing to the queue. Here should be some kind of logic of remembering which is the latest offset I have read of the events, in order to not reread all the events from the beginning when I restart the queue. But this is the best way how to do it. Event store should be the only source of truth in your system if you need to have the guarantee that you publish all the event to the queue, for example. Business log needed. So we have a client, and client says, I want to know who, where, and what did in the past over our system. In event sourcing, it's really easy, because you just add a performer to your event. A performer is the, for example, identifier of your system administrator, identifier of the user. And event sourcing gives your business event logs by design, because everything is an event. So we have the history of events over every aggregate. So in order to solve this problem of our client, we only implement the new read model, which is reading these events, and we provide some kind of audit log for finding who did what and when and over which entity. In, for example, relational databases approach, you need to have some kind of user table and user history table. And when you are making some change to the user, you need to update the state of the user and also emit some kind of entry in the log. Business is changing. The problem. I know that we are on the production. I have a great idea of the new outstanding feature. We need to use our historical data. How many 9 days do you need? This is the typical client approach when you had the system in production. What you can do? Sorry, client, we can't do it. We don't have the history in the database. Your feature can be implemented for the historical data because the only stuff we have in the database is the current state of application. In event sourcing, you have the events, which gives you this, which gives you the history of everything which happened in the system. So if there is if this new client idea is the change in the way how aggregate root works, you just re-implement your aggregate. When you read the aggregate when you want to run something over the aggregate, you just reply the events, but you are changing the function which is handling this new event, historical event, so you can rebuild your aggregate state. If, for example, the client comes with idea that he wants to have some kind of beautiful PDF reports for his other clients for about, for example, payments in the system, you just deliver the new read model, which is able to read the historical events, build the reports, and deliver the PDF reports for your client. And facing eventually consistency, client, you sold me this new event sourcing CQRS microservices stuff, and there is a typical problem which I explained before. When I add the new user to the system, I have created this, but when I go to the list, I cannot see it because Aggregate Root has persisted the event, but it takes a time to, for example, for a read model to update the list of this. So there are two simple solutions to solve this problem. So make expected change on the front-end side automatically. So if there are front-end developers and they get 200K status that the operation succeed, you can just push this, for example, new user to the list. So when client come back to the list, he will see that there is a user. So we just do some kind of mocking, inserting on the front end, but it's really easy. Another way is, for example, when you have button create and you get OK from your backend system, you can add here, for example, a delay for 100 milliseconds. Just to wait read model to handle these new events, and thanks to that, when your client will come back to the list, he will see also this user on the list. It can be easily done in, for example, new current technology which are widely used, for example, React Angular. Scaling right model. So if you will be facing a huge load on your system, so you want to scale your right model. So the most important part is that in this approach, we need to be sure that if we have a couple of machines, servers, we need to ensure that we have one instance per identified aggregate root. So if there is aggregate root Maciej, there should be only one instance in the server, even if we have a couple of servers, because if there is a load balancer on the top of the servers and there will be a lot of commands which are updating Maciej, and the problem is that if there will be a couple of different aggregate roots, the same aggregate root but on the couple of different machines, everyone will have the different state in the memory, and we will breaking the rule of the single writer principle. But there is some kind of mechanism called, for example, cluster sharding, which implementation is taking care of. So you can easily scale your system and your actors through the servers using cluster sharding, and it's implemented so you don't need to think about this. Scaling read model. So read model use different persistence solution. So you have different read models and you can add different storage on that. So you can easily add more transaction, for example, query service, and have one database over this. But you can scale it more, and you have database per each transaction query. So it's also possible with this kind of approach. So event sourcing and CQRS are very helpful architecture patterns, but implementing them in your system will give you a lot of profits, and they are very reactive. It allows you to do a lot of reactive stuff. You can separate them into different microservices. You have your model ready to be developed in the future. But you need to be aware of eventual consistency because this is the most problematic. I mean, it's a problem, but it's also a feature. You know it? So sometimes it can be a feature, some can be a huge problem. And when you're using this kind of approach in architecture, you are facing the challenges you have never faced before. So as I started at the beginning, when I was implementing using Spring, Hibernate, all this stuff, and I have everything blocking, it was really easy. And I need to get into the documentation. If something breaks, if I'm using this approach, I need to think about all the other parts, all the of the system. Oh, sorry. Okay, so thank you very much.